All right. So let me do this part here. You notice that here I have rho and s, okay? Then when and I had to take variation of rho and s. So what is delta rho? Well, delta rho is how it changes is given me by this thing. Okay? So delta rho will be given by delta rho over dn in the n, delta n plus 0 over ds delta s. And this will be mu delta n plus nt delta s. So the first thing is that to notice is delta s will, delta s, when I will take variation of delta rho, I will have a delta s here and delta s there. So theta will be related to the temperature. Okay? And then there will be this part here. And remember, the n is this, n is j alpha, j beta, g alpha beta divided by g. And g is the determinant of the metric. Right. So, okay, so this will be mu, and then I have delta n, which is dn over dj alpha times dj alpha plus dn over dg times delta g plus dn over dg alpha beta g alpha beta plus nt delta s. Right. Now, this is mu. And then I do this derivative here. This will be j alpha divided by ng. By the way, all this, if you have the notes, the calculations are in my notes, OK? So you can then see, even I don't write properly on the blackboard, which is really true. But at least the notes, LaTeX is readable. OK, ng, and then delta g alpha plus j nu. Then I had to do this n over dg. J nu divided by 2ng squared times, let me write it like in this form. I don't know why I wrote it in this form, but OK, let's keep it like this. Minus j alpha j beta over 2ng delta g alpha beta. So it's a bit, OK. Now this one can be further written as mu j alpha ng delta j alpha plus n divided by 2 g alpha beta delta g alpha beta, and plus n u alpha u beta over divided by 2 delta g alpha beta plus nt delta s. OK, some comments here. You see the part which has delta g alpha beta has u alpha u beta, which seems a good sign for which is multiplied by mu, and mu n is rho plus p, actually, which is a good sign that we are going to get what we want at the end of the day. OK, sorry, I had to go to this part. The video will, sorry. OK. Right. OK, so if we do delta S for the perfect fluid, we will get minus d4x, and we will get the square root of minus g times delta rho plus rho there's the variation of square root of minus g. Well, plus other stuff, okay? So let me focus only on, yeah, I know, okay. I should correct my notes, by the way, so. But okay, so there will be the variation of the other parts. Now, probably what I want to discuss here is the production of T mu nu, okay? T mu nu. Now, because T mu nu here, you will never see coupling between G mu nu and the other fields into this part of the action. So this part of the action will completely be irrelevant in terms of T mu nu, okay? Because my variable is J mu up. That's my fundamental variable. So this one, nothing here. There is no metric there.
We cannot make a covariance. The J mu nu we cannot write in terms of G mu nu, J mu.
Yeah. J mu nu was given before by yeah, but then you change your variables, and then you had to make sure, you know, like, so J mu, where did I write it? J mu is n square root of minus g u alpha. So if you write this one, it will be a function of u alpha, no? You will get square root of minus g. But then you change completely the action because you change the variables out of which you calculated the variation such. So I don't want to do that, okay? My fundamental variable here is j alpha. So I will have terms, but this will be, okay, let me put dpf only in terms of g, okay? So I completely neglect this plus. Notice that then I also can neglect this part of the variation, okay? Because this is variation with respect to delta J alpha. I don't care in terms of production T mu nu. All right. Right, so what I get here, then I will get minus 1/2 d for x square root of minus g rho plus p u alpha u beta plus p j alpha beta delta g alpha beta plus other stuff. Notice that also this delta s term I can neglect in terms of the production of T mu nu. Right. So you notice that. So you notice what happened here. Here I had u alpha u beta, and I have n mu n. And mu n is always rho plus p, but then there was also rho here. That with this variation here, so then I get only p g alpha beta. Okay. So and this is exactly what I wanted, right? Because this is exactly the T mu nu that we were looking for. Okay.
So I'm not getting it. If suppose I have this action, so how do we know that this J mu is independent of G mu nu?
Ah, very good. That's a very good question. So you have to fix from the beginning what are your fundamental variables. Given an action, it's not enough. You have to choose. For example, here I chose n to be completely dependent on the other variables. Okay. So from the beginning, you choose what are your variables. Those variables will lead to some equations. That's all. Now, it's true that when we have scalar fields, scalar fields don't have indices, right? So it's easy in a sense. But in presence of indices, in principle, we should choose. Now, yeah.
No, generally speaking, suppose I have this action in mathematical form.
Yeah.
So generally, if we vary, then we generally write this G mu in term of G mu nu, J mu. Then we have some term of J mu in covariant form. So but here you are saying that it is independent, and why we are choosing this J mu?
No. Okay, let me put it this way. So I wrote down a Lagrangian, okay? All right. So you write, so this is a Lagrangian, okay? Then you choose whatever fields. You say that n is this function here. Then you take a variation, that's all. N will depend on JA and NG, and G alpha beta.
That means J is depending on G.
Yes.
So if J is depending on root G, then it's function of gravity. So why we are not?
Hold on a second. N is a function of J alpha beta and J sigma. This is what I'm writing here.
You can involve the transformation and write J as a function of.
Yeah, but then you choose.
Okay.
And you say, okay, my independent variables are G beta only. That's it. Okay, so then I don't do that. Yeah.
Here, rho only sees the G, root under minus G, and you choose your action to that your scalar part or J part do not see. So what does it actually mean? You curvature root under minus G, you do not write it. You say told them to write it.
Sorry, what's the question?
Minus G,
Minus G.
yes, you see by only rho. You told, and you put it without this scalar field and with J.
So you're saying you neglected the second part.
I neglect this part here. Yeah, because here I want only to study this kind of thing. Okay? So here, J mu is a completely independent, this part, no? If I understood well the question. This part is a fundamental field, and there is no G inside here. For me, J mu is fundamental variable, and there is no G inside. So when I have to take variation with respect to G mu nu, this is 0, and this is 0. 0, 0, 0, 0. This doesn't happen. And you see there is no coupling with square root of minus G. So that part, in terms of G mu nu, doesn't give any contribution to the stress energy tensor.
Irrelevant for T.
Irrelevant to mu nu. What will happen to that part of the variables there? They will give you. They will give you, as I said, for example, like this part will give us a condition J naught. D mu is conserved, right? D mu J mu equal to 0.
So it means that if you vary this action with respect to J mu,
Yes.
so I think the J mu is very independent of this the equation you got.
Yeah, it's not very independent. I mean, so once you pick up your variables, I mean,
Because
okay,
also you
listen.
got that part
Listen, no. I think you have to think in a different way. So Lagrangian is variables and is expression. That's all. There is nothing more than that. You can think, okay, you start with, but what if I? If I means you're changing your fundamental variables. Okay, so there is choice of variables and choice of the form of the Lagrangian.
Eventually we have to choose.
Exactly. Right. Let me put for example. Okay. So suppose that I write down electromagnetism theory, and electromagnetism theory has Lagrangian, which is f squared, f alpha beta, f alpha beta. Then I say, okay, I take my variables to be f alpha beta. That would be f alpha beta equal to 0. That's your equation of motion you get. But now, if you consider f alpha beta to be function of a mu, then you get Maxwell equation. Okay? And then depending on the choice that you get a completely different, maybe completely different answers.
That means you have to choose action in such a manner that if you vary it, you should have equation of motion.
Exactly.
Like classical mechanics.
Exactly.
we are getting like-
Exactly.
Yeah.
So what's your name?
Sonal Desai.
Sonal.
Yeah.
Can I call you just Sonal?
Yeah,
Sonal
no
is
problem.
okay. So no, I think that's a very good point. in the sense, you see, this Lagrangian is just made such that T mu is that object there. And as I said before, all these constraint equations should lead to conservation of motion of this. Okay? So this thing we still have not seen, actually, okay? What we saw that T mu is the right form. That's one of the conditions. Because if I ask you, what is a chicken? Well, a chicken has to have, how you call it, wings, no? And, well, it doesn't fly much, but at least it can jump a bit, okay? But the point, so if you give me a Lagrangian, which gives me something which has wings and jumps a little bit, that's the chicken Lagrangian. So that's exactly the same thing here. We write down a Lagrangian here, which has exactly the same properties that we wanted for a perfect fluid. It looks complicated, and notice that it was introduced in 1974. So it took some years before they wrote it down.
So you are taking this the last two terms, because you want to introduce some scalar field perturbation and like this. That is the thing?
Yeah, yes. So, right. So in order to be able to describe all the perturbations in my perfect fluid, yeah, I introduce all this. Yeah. Yes. Notice that. Okay. So. Okay, I say this one, and maybe we stop. Or
Well, just speak for 4-5 minutes.
Okay.
Actually, you have to do these calculations a bit ahead. Then you come back and you will understand this too. So what these terms do,
Yes.
unless you do those calculations, you will not understand.
Now, the good point, okay, so you have in the notes, okay? So you can go over the notes. And if I may have done also some misprint in the notes and stuff. So please, if I do, please report to me. Something that I wanted, okay, so this thing of, now this is not really perfect fluid, but as far as I know, this was the first time that people discussed an action with only by means of scalar fields and this Lagrange multiplier. Okay? And you see, the question was, can I describe a general 4-vector u mu in terms of scalars only? And the question is yes. They did. So then it comes natural to say, okay, what about if I have a G mu nu? Can I describe G mu nu in terms of scalars? Oh, sorry, scalars only. Or any other object in terms of scalars only. Okay? Or maybe G mu nu, I can write it in terms of 4 vectors. 4 vectors. Okay? And so this question sometimes has been taken into account. You may have about Zuckerberg fields and stuff like this. So this thing came back, actually. This thing of using scalar fields to write something which is not a scalar field. So the first time myself, I was a graduate student, I read this thing, I said, impossible. Because how can you describe vector fields in terms of vector perturbation in terms of scalar fields? Impossible, actually. But then the point comes exactly as in the Zuckerberg fields point of view, is that because this object may have a non-trivial profile. I mean, it's a complicated object, actually. This is let me put, for example, this example, which is actually a true example, okay? Now, suppose I consider this field here, okay? Actually, these two fields here. So let me do the variation with respect to A. When I do variation with respect to A, I will get J mu, day mu beta, bi equal to 0. Okay? But at the level of the background, this is just J0, as we saw before. So this is dt. And this was a constant, if you remember well, at the level of the background. So this just says that the time component is 0. So B cannot be a function of t, but can be a function of x. We will never know. Oops. And then it comes the non-trivial thing. So B may have a non-standard profile, even in three-dimensional method Robinson worker. Okay, then you say, okay, but let's see what is the equation for B, actually, when I vary with respect to B. And you will see that this becomes like d mu, j mu, ai equal to 0, with a minus sign maybe, okay? But you know, this field here was leading to d mu, j mu equal to 0, right? When I was varying the L. So this thing just becomes, again, d mu, j mu, ai equal to 0. Again, only the time derivative must vanish. So even in this kind, so from the background point of view, it's not a very strong statement, this thing. Okay? In particular, one, you see that it looks like one has choices, right? Because, for example, I can choose B to be B1, I have two indices, no? I1 and 2, no? B1 can be, say, X, and B2 can be Y. That's perfectly fine. Okay? And the fact that the scalar fields acquire some non-trivial background value. And for example, I can set AI to be 0. But this is also consistent, right? Right. So indeed, choosing profiles, I will able then to build up vector degrees of freedom. Because what happens here is that this bi will become something like xi. So I will have like a kind of b can be put together to form a vector. Why did I choose 2? By the way, here I could have chosen also 3 or 4. I chose 2 for the following reason. 2 is the minimum amount of quantities that I need to describe vector modes. Because a vector has one longitudinal component and 2 transverse components. So the transverse component are what we call vector perturbations. And that's exactly what I need here. So in this sense, I am thinking here of a wave propagating along z, and xy corresponds to the orthogonal modes to the z direction. Okay? So in order to describe vector modes, I need only 2 scalars after I choose the direction of propagation. Okay? So yes, so then the background is not strong enough to say what is really this scalar field. You have a question? Okay, sorry. Oh yes, I want to say, maybe I say another thing and then I stop.
So are you saying that at the background level, okay, you have constants, but when you look for perturbation, they will become dynamic?
Exactly. So what, yes, that's a very good point. Okay, that's a very, very good point. Okay, since it's a good point, very, very good point, I say it now a little bit, okay? But I think I had to. Okay, so.
Just saying
No. Okay. Yeah. That's a good. So when I have, okay, let me put it this way. So this I have an action. Okay. Okay. Maybe this is a very good. Let me forget for a moment about this part of the action. Let me focus only on this part of the action. The reason is that there is no G mu nu. It makes life much easier. Okay. So I will have so I have, for example, I have these four fields coming from this part of the action. Okay. So then I suppose that I say, okay, so I have a background for which A1 is 0 and 0. And B1, say, is x, and B2 is y. We know that this thing satisfies the background equations of motion. So the background is done. This is a solution for the background equations of motion. Very well. But this is not enough, because I had to make perturbations. So this will have delta E1, delta B1, delta E2, delta B2. In general, I had to do this. Background plus perturbations. Now, strictly speaking, I don't need to consider this perturbation to be small. Okay? This could be just a definition. What I want to do now is actually to in general, this square root of minus g times L will be a function of my fields. Okay, so A1, AI, BI, and other fields. Okay? Now, other fields means G mu nu and all the other objects that I have. Now, suppose now this becomes a function, okay? This becomes a function which comes after the integral, d for x. So this is a Lagrangian density, we call it. This is Lagrangian density like this. Very well. Now what I do a Taylor expansion about this thing, about these small quantities. Okay, purely Taylor expansion. So I evaluated this L tilde when they are all 0. But you see, when A is equal to 0, this becomes 0 completely, right? So the first order term is 0. Then I have the linear perturbation, right? So this will be delta AI J mu d mu bi, right? This is when this one has a linear term, actually. Then we will have J mu AI d mu delta bi. And then, of course, I will have the part which relates to delta J mu and so forth and so on. But notice that this object here was just the equations of motion for the background, actually. So this must be background quantity, because this was already the linear part. So this automatically vanishes. So when I do this perturbation theory, when I expand the first order, I get the equations of motion. Okay? And this thing will be the equations of motion for, I can integrate out. So I can integrate by parts, okay? And I will get my equations of motion that we got before. So also this one will go to 0 up to a total derivative. But the crucial point is when I go to second order. So this was first order, actually 0 order, first order, and then second order. And second order, we will have this. For example, Now, this is background. This quantity must be background. But it's not 0. It just says 0 component. And this is this. So even A is 0, and we will get a non-trivial thing here, actually. Okay?
First order equation, right?
No, so this is expanding the action as second order in the perturbations.
Okay.
I will have, this is first order, so in total I have a second order. So I choose the perturbation to be first order in all the fields, and then expand the action as second order in those perturbations. And then I will get something like this, actually. The equation of motion will come from the first order part. No. So the background is background. Okay? When I say first order, I just mean in terms of this delta, if you want. In terms of this, think about here to have an epsilon thing. So
Finding the equation of motion for delta V, right?
this one will be automatically satisfied on my background, okay? Because, so what I'm saying here is that BI is x, or what do you say? B1 is x plus delta B1, no? So this is 0 dx, 0 that vanishes at first order. So this is a 0 order term, right? So this epsilon to the 0 term, this one. And this is epsilon 1. So if I expand at the first order, I will have a term like this, which is given me by the first order contribution from this one, times this one background. But this one automatically vanishes, right? Because this is G0 dt, but dt of x is 0. But this one no. So when I go as second order, I may have a non-trivial contribution from those fields. Even at the background, we're completely kind of invisible. Constraints only. Right. So what happens is that when we look for the equations, when we will look for, so this will set the constraints on dA essentially. Then dA will be not time dependent. Because BI only enters here. There is no other place where BI enters, except, yes, at this level here. Actually. Well, we will have maybe delta J mu nu, delta B. So, OK, one has to be, OK? But more or less, this is a story, actually. But I went a bit further into. So, yes, so.
So any question?
Why actually in the background, say, for example, you have scalar field, so why kinematic term is not really playing the role?
Kinetic field of what?
Like del mu phi, say your scalar field are A, B, Z.
Why there is no scalar field?
No, why there is no kinematic term?
Yeah. OK, so if you put, I mean, you can put,
Yeah.
OK?
In the Lagrangian
Right,
multiplier,
so you can put,
minus V,
right, but then you will not get a perfect fluid. Because you will get this thing. You will get, say, so then you will get something like this, square root of G, d mu s, d mu a square. But this will give a contribution from square root of minus G.
So in other words, there is no dynamical feature of the field you are not keeping?
Right. So this was similar to, I think, what you said here. But as I said, look, J mu is a Lagrange multiplier. That's clear. So then let's integrate it out. What happens? Here, J mu will be proportional to this phi, and inside n, this is Jj. So if I am able to integrate it out for any background, I will have a kinetic term.
Go up actually. If you do not have the kinetic term, then it will be diverse, maybe, because it will oscillate.
No, as I said, after you integrate out the J mu, you will have an effective kinetic energy, right? Is it clear, this one? J mu is a function d of the other fields. So you put back in the action, you will get.
That is a different thing. But you have just if you write the Lagrangian, you have the kinematic term, right?
Right. So,
A particular purpose they only.
right. So
Try to write in case of
so-
this, you can work
So
with
that's
it.
why I'm
So
telling that
you
for
you are
the
free.
fluid,
You are
there
free.
is, dynamics is not playing that role, right?
No, I wouldn't say this, because as I said, after you integrate the J mu, you will have some kinetic term for the fields. So this must be clear, all right?
But there if you keep, then already why you are not keeping del mu a term?
What? You not? Okay.
Del mu a, which is the kinematic term, that is.
Right. So okay. So okay. Let me put it this way.
Lagrangian is essentially that and the interaction potential.
Right. So okay. So yeah. Okay. So the question maybe also goes a bit to this thing there. This is the Lagrangian. Okay. So if this Lagrangian doesn't have any dynamics, we will see it.
Exactly.
If it
That's why I'm
has,
telling, so dynamics of the scalar field is not considered, but then you are telling in the J mu there is that dynamic.
no. Yeah. So what I say is the following. I mean, J mu will be a J mu will be a function of d mu something. This is the equation of motion that I have. J mu is a Lagrange multiplier, right?
Okay.
J mu is a Lagrange multiplier, and as such, I can use its own equation, put back in the Lagrange as it is. This is the Lagrange multiplier, right? Lagrange multiplier has no dynamics, and as such, its equation of motion can be used and put back into the action.
Wait a minute, but this constant is second class or first class? When you are first class constant,
No, this is not in the Hamiltonian formalism. This is through a nonlinear level.
See, as for example, no other current. See, you have no other current. So that basically follows why? Because it is you can write down the Lagrangian in terms of the total derivative of that.
Yeah. In principle, you would do.
So which you have no problem, right?
Yeah.
Total derivative.
Yeah, but what's the problem?
Right.
You have no problem. But my point is, what's the problem?
No, I'm telling so for this analysis of the background things, you really don't need the dynamical kinematic term that you don't need.
We don't need it. And if we put it, we would not get in general perfect fluid. That's perfectly fine. But we will not. This is not what I want.
you want, right?
Yeah, so according to your requirement, you are defining your
Yes.
action.
Requirement that time is 0. That term is 0.
Yes. So yes, this is the choice, just a choice of
That's the choice. This is not the general.
which is yes, but it's the choice that gives a general perfect fluid.
Yeah, that's fine. But it is not the
No,
general.
exactly. It's not general. Perfect fluid, it's not the general.
Consider scalar field, it has that.
Yeah. Exactly.
Okay, any other question?